Welcome everyone to today's very interesting seminar by Cristina Archer from University of Delaware. So Cristina Archer did her undergraduate studies as well as her master's degree in the Polytechnic Institute of Milan in Italy, where her thesis was on urban air pollution, modeling of urban ozone. So there is a feedback here. And then she did a master's in meteorology at San Jose State University in California, and her PhD at Stanford, where she became interested in wind power. Her advisor was Mark Jacobson, who is a leading figure and who's an atmospheric scientist or atmospheric chemist who has proposed and quantified the use of wind as a source of clean energy for more than 10 years. And after her PhD, Cristina worked for a couple of years as an atmospheric modeler at in the Bay Area Air Quality District, and which is very well known in air pollution history where a lot of ideas on air pollution modeling and control were developed. And then she became a faculty member at California State University in Chico in Central Valley. And since 2011, she is an associate professor at the University of Delaware. And she has published a very large number of very original papers on the use of wind power and properties of winds in the atmosphere. So I'm sure you will enjoy her talk a great deal. So let us welcome Cristina.
Thank you so much for the introduction. You did such a good job. I have no secrets for you guys anymore. You know everything about my life. So this is my first time at Stony Brook. Thank you so much for inviting me. It's my pleasure to be here finally and actually work with Brian finally in person and sit down with Matt and we do some work for DOE together. So it's really nice to be here. Today I have an ambitious plan for you guys. I want to talk about two topics, which is always a little difficult to do in a seminar, but hopefully it will be very natural and a smooth transition between the two. One is, they're all related to wakes, wind turbine wakes. And so the first part of the talk will be about some benefits that you can get from wakes if you are smart about how you lay out a wind farm. And the second part of the talk is again about wakes. How can you be smart about them and maybe use this dissipation that happens in wakes to your benefit during hurricanes? So that's the title of my talk, involves wind energy, turbulence, and hurricanes. So I definitely want to thank my collaborators in this, and Mark Jacobson was my advisor at Stanford, and we're still working together on a lot of wind power related issues. Willett Kempton, my colleague at University of Delaware, both of them worked with me on the hurricane work, and then Sina and Sengli worked with me on the array layout effects. So for those of you who are not too familiar with wind energy, this is my mandatory first slide, in a sense. I want you to get a physical and visual effect of how big the turbines are, how big these turbines I'm talking about. So this is a person standing by the blade. This is the hub, and this turbine is only 80 meters tall. Modern turbines now are even 100 meters or 120 meters tall. And this blade is about 50 meters. Now blades reach 77 meters. I think the biggest one is about 77 meters of length. So they're really big. And so when they transport them, this is what they look like on a gigantic truck. So this is a blade being delivered to a wind farm. And so as you can imagine, the overpasses in the US, they have a certain height, and so you can only build farms where you can actually go under those bridges with these gigantic blades. So the limit to wind power penetration in the US is actually the height of bridges, basically, today, because of these issues. For offshore wind energy, the traditional, I don't have a photo of the traditional turbines, which have a foundation that is in the water, and it's just a continuation basically of the pole all the way down to the bottom of the ocean. And those work down to maybe 20 meters of depth. But if you want to go deeper, then this is the dominant engineering solution, which is a quadrupod kind of structure, and it can reach 50 to 60 meters of depth. Past that, the technology is now floating turbines. And I was looking for a photo for you because apparently in Japan, they are installing some offshore of Japan. Japan is very deep, so they have no option but floating turbines. But I couldn't find one. But so they're happening. They're not just in the design stage. They're actually commercially available already. But again, let's go back to turbine wakes, to this turbulent structure that forms downwind of a turbine. And up to 2008, we couldn't visualize them. There were no photos of wakes. This is the one and only photo of what the wakes look like. And not surprisingly, every single talk on turbine wakes has this photo somewhere on it. Every single one, guaranteed. This one is a little harder to find, but I got my hands on it. It's the same farm. This is located, it's the Ormsreb farm here. So this is the Danish peninsula, and this is Sweden. And so this is this farm, and it's so unique. First of all, this is not a common meteorological condition. There are papers, and at least 2 papers, that try to describe why these wakes become visible. Why do we get that condensation? And I'll show you those next. But I swear to you, it's the only photo that I've ever seen of a turbine wake. And it's so beautiful, and you can immediately have a visualization of what it means. So there's the turbulence from the wake that propagates downstream, and then there's the turbulence from the next turbine and from the next turbine. And this is a case in which the wake expands horizontally a lot. This is actually a horizontal spread. In the vertical, they don't spread as much. They tend to remain elevated where they are. So here are a couple of papers that were published, and I'm showing them to you because one is a little bizarre. So they all agree that this is it's not a typical wind farm wake situation at all. In fact, it's the only photo available worldwide of a wake. So definitely unique. And the meteorological explanations can be really bizarre because we all know that to get condensation of air, you need to cool the air, not to warm the air. And here there's all this explanation that when the temperature of the wake rises more than about 1 degree, then the temperature in the wake enters the range that is marked in gray, so the favorable range, and condensation starts. So this paper is really a little bizarre. So basically stating that we got that wake because the wake got warmer, so very, I don't know how they published that. But nonetheless, it's a very unique case with this relatively warmer ocean for a very shallow layer. And then the turbulence in the wake mixes up things a little bit, so that air from the ocean, which is rich in moisture, and the colder air aloft mix down to the right level, and it's cooling the air, not warming, and you get that nice visualization of the wake. So, but why do we care about this? Why are wakes important? And hopefully by the end of this seminar, you will all change your research topic and work in wakes, because it's the coolest thing there is. So here's why they are important. I'm going to report some work that I didn't do. This is the work by Barthelme et al. And they had these amazing, I don't know how they gained access to all these wind farms data production, turbine by turbine, for a long number of years. But they looked at 2 wind farms, Hornsrud and Nysted. So both of them are in Denmark. And this is the layout of the Hornsrud farm, the one that we looked at the photo. And so the numbers refer to the turbines, so there are rows and rows of turbines. And they were looking at what happens to power production in a farm as I go deeper and deeper into the farm as a function of wind speed. And they looked at this wind direction, which is ER for exact row, so a perfectly westerly wind that is perfectly aligned with these turbines. So it's a worst case kind of scenario. The turbines are really like one after the other, perfectly aligned. And then plus and minus 5 degrees, plus and minus 10 degrees, and plus and minus 15 degrees. So what happens to power downwind? And this is what kind of happens. This is the power in the second row. So the second row is this here. The first row is the one upwind, and the second row is here. So what happens in the second row? And whoa, for the exact row wind direction, the power in the first row is 100%. So it's normalized. It's this line, it's 100%. In the second row, it's 60%. Just from one row, from the first row to the second, you lose 40% of the power. The wind is the same, the direction is the same, but only the first row can get the predicted power. The second row gets only 60% of it along the exact row. Plus or minus 5 degrees, still pretty bad, 70%. 10 degrees starts to recover, and then by 15 degrees, the negative deficit doesn't seem to happen anymore. Wow, 60%.
What's the spacing? How far?
Yeah, it's 70 in horse rev is 7. So D is the diameter, so they're like squares basically, and each diameter is about 120 meters, so 800 plus meters between each of them. And so what about further downwind? So that was the second row. What about deeper and deeper into the farm? Well, it doesn't get any better. So this is the exact row. This is the second row. Third row, fourth row, the power remains at 60% of what the first row can get. So obviously there is some importance here on these wakes. They really reduce the power that you can extract. And even for the plus or minus 5 degrees, still it still remains bad. Sometimes it keeps decreasing. Sometimes it flattens out. And even for 15 degrees, it's 70% deeper into the farm. And here, there's really not much of a recovery. There is a hint of a recovery here, and maybe here, but definitely this turbulence obviously impacts the productivity in the farm. Maybe it was just that study. Maybe it was just those two farms, right? Well, even older literature and older farms have the same behavior. So this is the average speed now, not power anymore. The upwind rows and all the downwind rows have much less speed. And also simulation results are shown in here. This was an older farm with much older turbines. I think it doesn't exist anymore. They've replaced them all. Now I want to talk to you about my favorite wind farm, which is Newark. This is located offshore of Copenhagen, but it's actually in Swedish waters. So it's actually a Swedish wind farm. And this is its layout. The north is this way. And it has 48 turbines. These are Siemens 2.3 megawatt turbines. And as of today, I believe it is the most tightly packed farm there is. So remember, horse rev was 7D times 7D. This is 3.3D times 4.3D. So this farm has a lot of turbines in a tight space. So as you can imagine, it has a lot of losses. So the wake losses are even worse than what we saw earlier. It's neat because there's a hole in the middle. So there are no turbines in here because it's too deep. And so, but it's interesting to study wake recovery because of the absence of turbines here. These two turbines kind of behave like upwind turbines because there's a little bit more time for recovery. So what about wake losses and Newark? This is actually a report that is available to anybody. It's online. It's not my work. It's actual data of power from the farm. And what they're showing here is kind of like similar to the Bartholomew et al. Paper. This is the first row for a 225 for a southwesterly wind. And they're looking at what the power is in this column, turbine by turbine. So the blue line is the 100% production or approximately 100% production in the first row. And then the pink line is the second row. It's turbine number 14, which is this one. And it has that classic shape that we expect to see with the maximum, the worst case at 30%. So remember it was 60% in the previous case. Now for the exact row kind of situation, we have lost 70% between the first turbine and the second. Amazing, huh? And then the other lines are the third turbine, fourth turbine, but the bad news is that it never recovers. So, you know, the further down you go, you're not gonna get any better. So it's still 70, 60% losses in the farm.
But it also appears that you don't get any worse.
Yes. Exactly, exactly. And then the most amazing plot of all, this is the only farm for which I can find information like this. So they were able to, they had meteorological information as well as power information. So they were able to really plot as a function of where the wind comes from, what are the losses that I expect. And as you can see here, that 70%, 60% is actually more like a fluctuating function, because for some directions there is that exact alignment and for some directions there is not. But nonetheless, you can go from 40% on average for that wind direction to 85% on average for that wind direction. So this is more like an average over longer times, and the plots I showed you before were for some specific turbines. This is an average for the entire farm. So major differences depending on where the wind comes from and where the wind comes from. I'm highlighting two special directions, 225, which is the southwesterly, it's a predominant wind direction, and 315. This is actually the wind rose that tells you how often these directions happen. And so the data support the idea that 225 is not a particularly good direction because the losses are about 60%, but 315 is a little better. You can get losses of only about 20%. So the northwesterly direction is better than the southwesterly direction here. And I will be simulating this farm, and I'll show you in a few minutes. The only other way we had to visualize wakes before that photo were these LiDAR animations, which are still relatively new. LiDAR is this technique that has a laser beam that is affected by particles in the air, PM, raindrops, bugs, any particle that's in the air. So the LiDAR measures the backscatter from that particle, and it can tell you how far that particle was, and from two subsequent scannings, it can tell you how fast it moved, because it can track the position of the particle at two different times. So tracking particles in the air, and with a lot of data manipulation and algorithms, the LiDARs can actually tell you what the wind speed looks like. And this is such an animation for a southerly wind. Basically, there are four turbines, 1, 2, 3, 4, and you can see their wakes as reduced wind speeds. So the speeds behind the turbine in the wake is reduced, and this is kind of like an approximate scale. So upwind is 10 meters per second, and downwind it can reach the dark blues, which are 2, 3 meters per second. So here's another visualization that I'm not talking about funky numbers. This is really happening, and they're actually measuring finally some. This is over land, and I think this image is from this farm offshore. And unfortunately, I don't have the scale of what that wind speed is. There are also numerical simulations that have been done with the WRF model to try to simulate the impact of these farms. Obviously, the WRF doesn't have turbines in it, so you have to parameterize their effect. But what they did, Fitch et al. In this study, they had a very large farm, which is on the order of 10 kilometers by 10 kilometers with hundreds of turbines in it. And they simulated a bunch of cases. And this is a daytime case, and this is a nighttime case. And this is the deficit, the wind speed deficit downwind of the farm. So not only can you have a wake from a turbine, you can have a wake from a farm. And these wakes can actually propagate pretty far downwind. So In this case, during the day, the scale is about 80 kilometers here. So this wake is visible 60 kilometers downwind. And during the night, it can even be worse. So the deficit can be higher, so in the order of 3 meters per second, and it can propagate even further downstream. So these are model results. So what I decided to use was, instead of using the WRF, I wanted to use a code that was better for turbulence, because that's what the wakes are. They're turbulent wakes. And so having learned that I don't want to reinvent the wheel, I don't want to write a new code from scratch, so I was very smart about it. And so I talked to NREL, the National Renewable Energy Lab, and they had just developed this code SOFA, which is the software for offshore, onshore wind farm applications. And I still don't know for sure if offshore came later or onshore came later. I think they first did it for onshore, so that could have the O to make SOFA become an acronym that can be pronounced. Yeah, I think that's what it was, onshore first, and then they added offshore, and now they're stretching offshore more than onshore, but anyway. This code is based on C++, unfortunately, which is possibly the only language that I think I've never learned of the 60,000 that I've dealt with in my long career as a graduate student and professor. And so it's a little hard for me to debug this beast. But anyway, it's a nice package and it's very advanced. So the blades are actually simulated. Each blade is actually resolved by about 40 points. And so we have the 3 blades that rotate. So I can simulate the rotation of the blades as a body force basically on the flow. And another neat feature is the treatment of the boundary conditions. So most of the LES studies that you will find in the literature have periodic boundary conditions, because those are easy to implement, and that's the advantage. But when you have a wind farm, if you have periodic boundary conditions, what it really means is that you have an infinite farm. Because if the flow that comes out from the end of the farm comes back at the beginning, it's kind of like having a really gigantic farm. And so an infinite farm is not exactly something that is easy to relate to. But SOFA allows for imposed boundary conditions. And so I decided to simulate Lillgrund, the same farm, with a domain that has 4 kilometers by 4 kilometers by 1 kilometer. It doesn't sound like a lot, but I have 18 million grid cells. These simulations are very, very computer intense. The resolution is down to 3.5 meters around the blades and 7 meters in the rest of the domain. And I'm telling you these details because it takes me 45 days to get the results that I will show you for each run. But all I'm simulating is 2,000 seconds of simulation. So to get 2,000 seconds, I have to run for 45 days times 24 hours times 60 minutes per hour times 60 seconds per hour to get 2,000 seconds. Not fair. But I'm planning to try to speed up this process. So of course I picked the southwesterly prevailing wind direction 225 that I mentioned before. And I'm initializing with a 9 meters per second wind speed and 90 meters. And what I wondered was, okay, we have this nicely packed farm, which obviously has a lot of wake losses. Can I do any better? Can I do anything better? Would it be better to lay out the turbines in a different way? Would I get any benefits somehow? So I compared the control case, which is exactly as it is today, with a staggered, STG for staggered case, in which, I don't know if you can tell, but the even rows are shifted by a tiny bit. So if you compare this row with this, turbine number 7 is not aligned with 6 anymore. It's actually shifted by 3.3 diameters divided by 2. So I shifted by half of the regular distance. And so what I obtained this way is that for the 225 direction, in which the control case had a perfect alignment, was the exact row kind of situation. Now it's not, because every other turbine is out of the way. So hopefully this should produce more power. And this is what the wind speed at 90 meter looks like. This is an average wind speed for all those 2,000 seconds. precious 2,000 seconds. Oh, and that's, by the way, 45 days if all goes well. If your cluster doesn't go down, if you don't have any, all those things. So this is U mean. So the mean speed, where the reds are 10 meters per second and the blue are 3 meters per second. And not surprisingly, we see these nice wakes with strong deficits, very weak wind speeds downwind in the blues. And in the control case, you also see some kind of a, there's like a channel where the wind speed remains a little higher. And then every turbine downwind pretty much is exposed to relatively weak winds because of these wakes. In the staggered case, it's much better because turbines are more likely to be exposed to higher winds and so produce more. So did it work? Yes. So here's the average power. So what I did was the total power of the farm averaged and then divide by the number of turbines. So each turbine is rated at 2,300 kilowatts. 2,300 is the rated power, and I'm getting about 700. So about, a 30% capacity factor for this configuration, for the control case. But look at this, for my staggered case, I get 787. So almost 100 kilowatts more. So definitely a large improvement in the capacity factor. And then the array losses go from 35% to about 20%. So this is definitely beneficial. And all I did was stagger so I'm installing the same number of turbines in the same place, the same brand, the same rated power. Instead of putting in position A, I put in position A plus a tiny bit. So the costs of making these two farms should be the same. And then, of course, you can have fun, right? And then you can say, would it be better to space them more along the prevailing wind? So here I took out every other row. Or would it be better to space them more across the main wind, keep the same number of rows, but space them more, space them and stagger them, space them twice as much in all directions? Which one is the best? So I did all these simulations, each of which took 45 days. Some of them were in parallel though, so they could go at the same time. And this is kind of like, this is the time series of the power per turbine, again, divided by the number of turbines. And the control case is the blue case. And it's pretty much the worst of all of them. So pretty much every other configuration that I did had higher production on average than the control case. This is, again, not surprising because that farm is so tightly packed. So as soon as you start spacing the turbines more, each turbine produces more. So it's not surprising, and the Lille Group people knew this. They wanted to have the maximum power possible, or so they thought. They didn't care about the productivity per turbine. And I'm gonna skip this one. You can try to quantify if it's better to space this way or that way. I just wanna show you some other trade-offs, which is more interesting. So cool, you can stagger along that direction. Well, what happens when the wind comes from the other direction, like 315, which was another important wind direction? And so I have the original layout. Now all the turbines are facing the wind from the northwest. The turbines can do that. They can always orient themselves to face the strongest winds. And this is what they look like in the staggered design. So this is the same staggered farm that I showed you before, but the turbines are facing northwest. And these are the average wind speeds. And so the average power of the original layout is actually slightly higher than my staggered layout. Did it. And the losses were a little better too. But the change is really small. So 964 versus 939, it's almost minuscule. It's a very small loss. So you need to now pick your direction. In this case, the 225 direction is more dominant, so it's more beneficial to go with the staggered layout. But if you were in a different farm and this situation was the wind from the northwest was more common, then you might want to stick with the original layout. But the bottom line is that there are all kinds of trade-offs, and it would be great if you could make these decisions before building a farm. if you had all these options with you, and here I have 9 results from simulations, and I'm still struggling to find a way to show you everything in one plot, and hopefully this works okay. I have the number of turbines from left to right here. So some cases, like the control case, have 48 turbines, and some cases have 12. So that's what the x-axis tells you. On the y-axis is actually the power generated per turbine. And so in the control case, you remember it was something like between 600 and 700, and at 315 it was higher, as also the observation showed. And then the area of this rectangle is the farm output. So the bigger the rectangle, the more the total output of the farm is. So visually, you immediately see that the double spacing in both directions is very efficient. Look at how skinny this rectangle is, because the power per turbine is very, very high. But you only have 12. You only have 12 turbines, so the power that you can generate is only 10 megawatts compared to 33 that they get today. So the Delaware people really wanted 33 megawatts rather than having these amazing efficiencies. But maybe if they were to redo it today, here they spend, a quarter of the money. They only have 12 turbines. But they don't get a quarter of the power. They get a third of the power. So with less of an investment, they actually get more for each dollar that they invest. So these are the kind of trade-offs that I think would be good for developers to have in their hands up front. And then they can pick which design and which matters more to them. And those cases were under neutral conditions. I think I forgot to mention that. But I finished actually the unstable runs. I'm post-processing them right now, so I can wait to see what happens under unstable conditions. And then there's the beast, the stable conditions. This is the nightmare of every turbulence model, because under stable conditions, the turbulence is so suppressed that you need to really resolve it well. So the turbulence is little, and so it matters a lot how you parameterize it. And so right now my code, I cannot even compile the code right now for stable conditions, but hopefully the results, at least qualitatively, hold. I'm not expecting that the results only hold for neutral conditions, basically. I'm expecting some effect of stability, but not the main conclusion to be affected that much. I still want to prove it. So in summary, for the first part, I used LES to try to quantify these trade-offs. And I'm a proposer, a supporter of this staggered layout. So nobody says that the turbines have to be aligned along the prevailing winds. It seems like most of the farms are. And actually, you can really design the shape that you want. We're looking at some different shapes, and it appears that having a hole in the middle might actually be a good idea, because the turbines in the center of the farm don't produce that much anyway. So you might as well not have them and allow for some recovery in the farm. I'm still looking for some kind of a simple way to summarize everything, and I think I'm close. But anyway, wakes are important, right? The turbulence in the wakes reduces the wind speeds. And so in the layout, we're trying to take advantage of that knowledge and design farms that are smarter. But now I kept telling myself, okay, I'm reducing the winds, is there any positive, can I take advantage of the fact that the winds are reduced downwind? What happens in a hurricane? This was more like an academic exercise at first, but what happens if you have all these wind turbines on the path of a hurricane? I'm expecting that the winds will be reduced. If they can reduce the power by 70%, can they do this under such strong winds? So for this question, we needed to be able to simulate an entire hurricane. So obviously my 4 kilometer by 4 kilometer domain that takes 45 days for 2,000 seconds wasn't gonna cut it. So I used Mark Jacobson, my former advisor, used his model, the Gator GC-MOM, which is a sophisticated meteorological and air pollution model that has the best particulate matter simulator. And so it resolves all kinds of processes and the winds. So it's not just a wind model, it's much more complex than that. We implemented a wind turbine parameterization. So in the low, we pretended like there was a turbine in the boundary layer, and this turbine intersected 5 levels, 1, 2, 3, 4, 5. And depending on the fraction of that circle that belongs to each level, we removed kinetic energy in that level proportionally to the size of that sliver of the rotor that was in that level. And so, actually I have the next slide that tries to summarize that. So I know how much power each turbine is generating as a function of wind speed. I know that during a time step, it's extracting a certain amount of energy given by the power times delta T. So I know that this kinetic energy has to be taken out of the model because that's what the turbine does. And so I need to adjust basically the prediction for wind speed for that kinetic energy reduction. And it's actually relatively straightforward to do this way. And again, the redistribution of that kinetic energy removal was done proportionally to the rotor area in each level.
It's just a naive question. So those turbines can be operated even under hurricane wind?
I'll talk about that.
Yeah,
I'll
okay.
talk about that. And so what we did was we initially did Katrina and Sandy only, and then the reviewer wanted us to do yet another hurricane, but I'm going to focus on just Katrina and Sandy today. And what we did was we placed huge wind farms along the Gulf Coast and along the East Coast. So I'll show you. Actually, well, these are results already. So let me go to the next. Okay. This is Katrina prior to landfall in the case without turbines. So we're just trying to simulate the hurricane. And we placed turbines between land and this red line. This is a strip that is 100 kilometers from the coast. And it's all the way from the tip of Florida to the Texas border. And in this case, the control case has 500,000 of turbines. Okay, so by comparison, today worldwide there are 50,000 turbines. Okay, so this is 10 times the current number of turbines installed worldwide. Enough to power half of humanity electricity needs. Okay, huge wind farm. I hope you got that point. Huge wind farm. All right.
That's more than a single row by far.
Oh yeah, it's yeah, and I'm spacing them 70 times 70. So basically, you take we needed to figure out how many it is. So we did how big this area is, 4D times 70, and that gives me the number of turbines and everything started from it. And so this is what happens at 2Z with turbines. No turbines with turbines. So you can clearly see that in this strip of I was about to say land, of ocean, the wind speeds are obviously reduced. The colors are purple, which are between 5 and 10 meters per second. They were more like in the blues and the 15 to 25 meters per second before, and even some yellows and some points between 30 and 35. This is actually the wind speed difference, so you can clearly see where the farms are located. And this is the sea level pressure difference, which is not dramatically different yet, but it will get more different later. So this is prior to landfall. And this was really amazing, how much weaker the winds are here than before. And then this is landfall. And you can see that those reduced winds from the turbine case actually have made their way here, this sliver of weaker winds, have made their way into the core of the hurricane, and they've actually kind of split this is wind speed, so it's not pressure or any kind of dynamic feature, but it shows that the weaker winds have actually affected the core of the hurricane a little bit. And so you can still see where the maximum reduction occurs. And then in this area, there really isn't that much reduction because these winds are actually too strong and the turbines are not operating. But they are operating at the edges of the hurricane. So these turbines only operate when it's realistic and are shut down when it's not. This is the wind speed difference, and now we're starting to see some effects in the sea level pressure. So this is up to, I can't read it, it's about 30 millibars higher pressure in the center of the hurricane with turbines than without. 30 millibars. And then lastly, after landfall, the effect continues, and you still continue to have weaker winds in the coastline here, and the hurricane hasn't changed its path. It hasn't changed where it's going. It has become weaker in the center, but it's still a category 1 at this point. And that's identified by the highest winds that you can find everywhere in the hurricane is still the same. So this has not become something else. It's still a very respectful hurricane that can cause a lot of damage. But in most of the coast, you have never actually experienced winds that were higher than about 30 to 35 meters per second, as opposed to 50 to 55 or more. For Sandy, the results were less striking, partially due to the fact that Sandy was so big that even though this is a 400,000 case, so slightly less, but Sandy was really massive in terms of size. And also at this point, the winds were actually coming from the shore, so the effects are a little less because it was less beneficial in general. But nonetheless, we got wind speed reductions and some effect on the sea level pressure. So this was exciting, and it became more exciting when we started to see what the effect of the reduced winds would be on storm surge. And this is a very simple approach, and I want to say it up front. It's not the most sophisticated approach at all, and in fact, I have a proposal pending to do a more complex storm surge modeling. We did a diagnostic equation, basically, and the idea is the simplest idea, which says that the height of the storm surge is driven basically by the stress over the ocean surface, and this stress is actually proportional to the square of the wind. This is well known from textbooks. And so, as you can imagine, since the winds were so reduced, and there's a V-square effect here, the effect on the storm surge is actually very significant. Everything at the denominator is constant. Basically, it's just the bathymetry. So we have a function that is proportional to the square of the speed of the wind, the fetch, and the bathymetry, and the fetch can be easily calculated from model results because we have all the information about the maximum radius of influence of the hurricane, as well as the velocity of forward momentum. All these parameters are easy to calculate from the model. And so the storm surge results were incredible. So I want to show you an initial summary of that. And unfortunately, I'm switching from the nice pictures to less user-friendly tables. I can't avoid it. I have to show you some numbers. So let's take a look at Katrina simulation A, the control case, the control case with turbines. Storm surge reductions between 23 and 79%. So by placing those 500,000 turbines along the Gulf Coast, basically there was no flooding in New Orleans. The wind speed, the peak 15-meter decrease, so the point in the entire domain with the maximum reduction in speed was 40 meters per second decrease. So the speeds went down by that much. The power delivered was on the order of 1.5 terawatts. The humanity consumption of electricity is 3. So I wasn't joking when I said half of humanity needs. The number of turbines is here, the spacing is here, and this is the question I'm going to try to answer now, the cutoff wind speed. The concept, so basically turbines today are rated to sustain 50 meter per second winds. So they're built, the engineering code, there's an acronym that I don't remember, says that they need to not be destroyed by winds that are 50 meters per second, up to 50 meters per second. So they're guaranteed to resist those winds. But they don't operate at those speeds. So the way they operate is that at usually about 25 meters per second, they actually stop spinning. So when the wind hits this cut-off wind speed, they stop operating and they don't turn anymore. So in these simulations, the initial ones, we assumed that the cutoff speed, instead of being 25, was actually 50. So it was like, let's look in the future and see what would happen if we had turbines that were actually able to produce power between 25 and 50. So right now they don't, but we assumed that they would. But then we wanted to explore how much that assumption made a difference in the results. And so we're trying to see what's the effect of this cutoff wind speed. And again, the red line is the power curve of the Enercon turbine. This one is a new generation turbine that can actually operate up to 34 meters per second. 25 is the cutoff of the repower turbine. It's another turbine that I used. And it's most turbines are shut off at 25. This one is shut off at 34 today. So this is not a futuristic turbine. This is today's turbine. And then it produces no power all the way to the, let's call it distraction speed, this 50 meters per second. So in the first results, I assumed that it was able to produce power all the way to the distraction speed and then produce nothing. But then I was like, well, let's see what would happen in simulation C for Katrina. I actually kept the cutoff wind speed at 34. So this is today's technology. What would happen? And the storm surge was still reduced dramatically. Instead of 23 to 79, it was 26 to 75. So these are percent reductions. So it kind of depends. So they refer to the fact that as the storm evolved, storm surge went up and then went down. And so I have an original curve and then the curve with turbine. So the reduction, it kind of like depends on the time. And so that's the range, between 23 and 79% for the control case and 26 and 75. So it still went down significantly. And it didn't even impact the delivered power that much. Basically, there were so few hours and for so few points, the wind speeds were actually between 34 and 50, that it really didn't make that big of a difference. Yes, I mean, I would rather have 79% storm surge reduction than 75, but it's still a very dramatic reduction in the storm surge. So increasing the cutoff might be desirable, but it's definitely not necessary. And then we're like, what if we used a different turbine? What if instead of the Enercon 7.5, we used the 5 megawatt repower turbine? So we changed that, and the results for Sandy, so now this is not Katrina anymore. So for Sandy, the reduction was between 24 and 34. Now the reduction was between 27 and 32. I usually focus on the maximum number. So, you know, it was a little worse, but by no means the results were altered. The main conclusion still remained. So this
Doesn't
turbine,
a lot of that say that it doesn't matter very much whether the blades are rotating or not? When you lock them, they still
yeah,
produce
so
weight.
that previous result, yes, that's
Yeah.
what it kind of implies. It says that it might not be worth it to try to invest in a stronger turbine that can sustain those winds, because even if you stop it, you still get the reduction.
Well, you
This
could,
one
you
is
could
more
put
about
up things that aren't turbines at all and get the same effect.
So that's
Which
not-
Forget
ones?
about the generation.
So that's not
just
true.
total-
I think the
I
effect
don't
is
know.
because
Well-
it is because the extreme winds occur at very small
Yeah.
number of times. So it's not that, I think your statement that if the turbines were not rotating, then it would be the same effect. It's not like that.
I thought he meant that he could get similar effects with alternative technologies.
No, with
No,
no
just put
turbine.
up fake windmills without rotating blades.
Okay. Well.
Just a lot, something that stirs up a lot of turbulence.
Well, I haven't done this, but I would like to see what would happen if the turbines were still spinning, but maybe not generating, because the speeds could be so fast that they damage the generator. But even if something spins, it's still extracting momentum from the atmosphere, because the momentum goes from the flow, from the air to the blades. So it would be better than just standing like that. But this was more about investigating. So if you have what's the dependency on how the rated power of the turbine? So I just wanted to make sure that my results didn't depend on using this Enercon. Okay? Even if I use another turbine, it still works. But of course, this turbine is rated 33% less. Instead of producing 7.5 during the storm, it produces 5. And they're about the same size. So they're not exactly the same. This is slightly smaller, so that's why I have more turbines, because I can squeeze more in the same area if they are smaller. But the results still hold. And then the question that everybody asks me, you know, nobody's going to build 500,000 turbines, right? So what's the minimum number that you need? And I don't have that answer yet, because these simulations took longer than 45 days each. It took a long time to get these simulations to finish. But I did look at the effect of what if I cut down the number of turbines by half. So for Katrina, from 543 to 271, and for Sandy. And these are the final results in the storm surge. Obviously, there is less of a benefit because now we learned something about wakes, right? If you space them more, the wakes influence the flow less. And so obviously there's a disbenefit, but it's not invalidating any of the results. They still hold. So instead of 23 to 79, it's 19 to 63. Instead of 24 to 34%, 17 to 21. So doubling the spacing reduced the power production by less than half. So this suggests that there are some nonlinear effects that are going on. So it's not that if I cut the number of turbines in half, I produce half as much power and I produce half as much storm surge reduction. No, it doesn't work that way because it's nonlinear. And so the storm surge reduction is much better than a half. And even the power production it didn't go down by half. It went down by less than a half. And then lastly, I wanted to look, so I went down to 78,000 turbines from 543, on the order of 10% of the original value. But I placed them, so they're less, way less than before. But I placed them strategically, not everywhere along the coast, but just upwind of New Orleans, with the idea that, let's say I just want to protect the city of New Orleans. Do I need to have turbines in Florida to achieve that? Do I have to build turbines in Texas to do that? Or for Sandy, do I need to protect, if I want to protect New York City, do I need to build in Delaware to achieve that? So these simulations, which I call the wind farm location effect, they're trying to explore the dependency on the location where the farms are, and they have way less. This is a quarter of the turbines, and this is about 15% of the original number. And again, the results seem to still hold. You still get a lot of benefits, even with these reduced numbers. So I don't know if there is a minimum number that produces no benefit, but it's what I'm hoping to do more research to answer that question. So in summary, these results are astonishing, and we were actually able to reduce wind speeds really dramatically, up to 41 meters per second. I think actually one of the simulations had even 44 meters per second reduction in some locations. This is not to say that the hurricane category was knocked down by 4 or 5 categories. This is the maximum reduction that I obtain at any point, but the hurricane remained a hurricane. So I hope that I'm not confusing you with these numbers. But these reductions, the highest ones, are where the turbines are and downwind of the turbines, which means along the coast. So you get these very strong reductions where you want it, where the people are. And the amazing results were the storm surge results, which were, I have seen no proposal for New York City recovery after Sandy that can reduce storm surge by 70%. The local arrays can provide local protection. This is what these smart location simulations proved. So I can still protect New Orleans and New York City by placing turbines in New Orleans and New York City. I don't need to ask taxpayers money from Florida to protect New York City, which will never happen, right? Obviously, higher rated turbines have higher benefits. And if you can operate the turbines past the cutoff speed, that's great, but it's not necessary. It doesn't invalidate. It's not a necessary condition. And that's all I have.
Thank you. And so let us see if there are questions that returns.
Do you want to direct the questions, or
Yes,
should I go ahead?
yeah.
Okay. Go ahead.
So, Adi,
Hi.
so who has a question?
How much would 500,000 turbines cost, and how does that compare to rebuilding New Orleans from the ground up?
So you do the calculation. So each turbine offshore is about $2.5 million per megawatt. So those turbines were 7.5 megawatts. So do 7.5 times 2.5. That's the number of millions per turbine.
And then 500,000.
Yeah. It's
So
probably
we're looking at about
110,000.
about $10 trillion.
Yes.
About a third, or 2/3 of the U.S. annual GDP.
So by comparison,
I think that's quite a bit less than rebuilding New Orleans from scratch. So we might as well just let it.
no, I mean, it's a huge number, but I mean, building the seawalls offshore of New York City, just seawalls, which would not generate power, enough power to power humanity and all of that, they cost between $8 and $20 billion just for New York City. So just to protect New York City with seawalls, which have no energy benefits, they don't reduce the carbon or transform the economy. Just seawalls for New York City alone is $8 to $16 billion. So
a factor of 10 less, or a factor
Yeah,
of
but
about
it's
1,000 less than.
Actually,
no, but it's just building in New York City.
35%.
So if you were to build it along the coast, then it's actually, I mean, it's comparable. Plus, if you have to build seawalls, you really have to come up with the money, and there's no revenue profits that comes out of it. So you really have to take taxpayers' money and build the seawalls, and that's it. Your money's gone. These things generate power, profits. In 10 years, they're actually making money. Isn't that crazy? I mean, it's. I'm telling you. Okay, sorry. Go ahead.
So there is
Yes.
a question in the back. Yes.
Oh, hello.
I think presented some very interesting results, and one conclusion seems to be quite counterintuitive. To be honest,
You have to.
I think there was actually a question that was discussed before when you were doing your presentation. That even when the turbines are turned off, are not operating at all, still it would not affect much the effect of these turbines. And that, I think, related to the last conclusion, probability has a couple of speed is desirable but not necessary. But I think the way that you take account of the effect of winter turbines on hurricanes, and hurricanes is a critical component is the way that you extract kinetic energy from the hurricane. Remember, you have a formula that the wind speed at next time step is equal to the square root of 2 times the difference, the critical kinetic energy at the previous time step minus the energy, creating energy that is extracted within this time period, and then divided by the mass of the air volume. Okay, but this would be you when the turbines are not working, you need to turn off this equation. Then you will not be able to extract the kinetic energy from the hurricane.
Yeah.
And I think that the effect would be less. Because then what would when the turbines are just standing there, the effect of the turbine on the hurricane is still there, but it would probably be much smaller.
No, I have to stop you before you go too far. Everything you said is correct, and yes, when we are past the speed, that term is 0. So the extraction of delta E is nothing because I have no effect at that grid point where the wind speed is above the rated speed, right? What about the next point? What about the next point? Oh, the surrounding points. So So this is in the model. So in my model, it's doing that. So when that point has a wind speed that is above the rated speed, it's not extracting anything. So the hurricane behaves as it would without a turbine. I'm not even taking into account the little drag that it would have. I don't even count that. But the effect remains because of the surrounding points. Some points are below the rated speed. And actually, if you think about the hurricane per se, these very high speeds above 35, they're only found here. And when the hurricane hits here, actually, let me show you the one with the line. You see that here the wind speeds are very high and there's like a bump where nothing happens. These are turbines that are not spinning. And so they're not extracting anything, but the rest are. So individually, every turbine has the behavior in that equation, but when you think about the farm, the chance that all the turbines in the farm will be experiencing winds above the cutoff is very small. And also, because of this feedback, so the weaker winds make their way into the hurricane, then the hurricane is weakened, it's tamed a little bit, if you wish. So as it approaches the rest of the turbines, it's actually weaker than it was before, and it actually reaches these very high speeds very few times. That's why the benefits remain. It's not that I didn't include this effect, it's actually in there, but the rest of the farm is still extracting all that kinetic energy. Make sense? So you have to think about it spatially, not just as one turbine, but as a...
So there is another question here.
When talking about the efficiency of the wind farm, there's another dimension occurs to me, because wind turbines have different heights. So how about using different height of turbines in the same wind farm? But actually that...
I'm not, I love that you're asking this question. I just think you're brilliant. Yeah, I mean, I'm staggering in the vertical as well as in the horizontal, and I can tell you the results if you want. So if you guys remember that the second row is just, it's bad, right? And so I thought, what about building lower turbines in the second row? Because it's already so bad. So I don't need to spend all that money to make tall turbines. So I can save some money on building and materials. I make the second row and the fourth row and every even row lower. And the third row, I make it the same. And what I got was a little bit more power. Actually, not even equal, but a tiny bit more power than in the original case. But now I'm building turbines that require less material, they're built quicker. And so let's say I get the same power, but for less of a cost because of that effect. So yeah. Then you can play, right? You can play every other one.
So there is a question about, I think.
So you use V squared to represent the wind stress in your calculation of storm surge. Have you tested other drag coefficients and other calculations? Well, basically use different drag coefficients to calculate the wind stress. Because in these environments, is the accuracy of V squared in proportion to wind stress? It isn't very accurate because there's a lot of nonlinear effects and waves on the transfer momentum from the air to the sea. So I wonder how that would change these results.
So I'm not an oceanographer, but my understanding is that the V-square relationship is actually very strong and holds at all times. It's the coefficient of drag, CD, that may vary. Is that consistent?
That's what I'm saying,
Yeah. And so what I'm calculating is actually the change in height, and so it kind of goes away. So the drag coefficient kind of goes away because it goes into this constant. Oh, I see what you're saying. It's not constant.
Yeah.
It's maybe not constant.
Well, it varies with the wave height.
I mean, we had wave height incorporated because wave height is proportional to the wind speed too. So in a sense, it's kind of the same phenomenon.
Yeah, there is some
I guess I'll take that, and I haven't looked at that, but I want to say that I don't. So the question is, which value of V do you use to calculate the storm surge in New Orleans? This is for just the two cities of New York and New Orleans. And what I did was I used the average wind speed over the sector of the storm that was upwind of New Orleans, trying to reproduce some kind of a fetch effect. So it's not like I picked a single point. I didn't pick the speed at New Orleans. I tried to keep some kind of an average over a large area to try to reproduce that batch kind of effect. So this is very simple, but I'll think about it. Yeah, thank you.
So that's another question.
I'll come back to you, but you already talked, so.
I was just wondering, like, I know the turbines you discussed are like placed in the ground, but how about the floating turbines? How do they maintain their position during a hurricane?
Yeah, that's a great question. So as you can imagine, I didn't worry about the technological details, so I don't know.
Do you think they would anchor it or something?
I think that the depth actually in these regions is not very deep, so it's possible that we can get away with foundations, traditional foundations for a long way. So yeah, if there was, I suspect the floating turbines and hurricanes don't get along very well. I guess.
So Malcolm.
The Rockefeller Foundation is currently holding this big competition called Rebuild by Design. I don't know whether you entered or not.
I didn't, but I'm working with Alan Blumberg, who is, tomorrow they're showing the projects. Yeah.
Well, that was my question really, because he's another what you might call futurist, whose idea is to build a new coastline offshore from Cape Cod all the way down to Chesapeake Bay, right?
I think it's smaller than that, but
you know,
anyway. Yeah.
Moving billions of cubic yards of sand, and then there are wind turbines on the. So you're part of that.
No, I mean he invited me to these presentations that they had, and then after seeing my presentation, he added the turbines. But it's not essential that there are turbines on those islands.
I know, but I mean you have 500,000, but he just has maybe 12. But it's just to show multi-purpose of a new coastline.
Yeah, that's what it was. I mean, he wasn't tapping into the speed reduction of one row of turbines necessarily.
The real question is, what is the state of Delaware doing about offshore wind power? Are they actually making any progress?
Not much.
Nothing.
So there was a proposal by Blue Water Wind a few years ago. It was so close, and then it didn't happen. I don't remember.
They came here and talked about it.
Okay, oh good. And so it's not happening offshore of Delaware.
What's the problem? Is it?
I actually don't know, but then our university, we had a proposal to build a test site to test offshore turbines, 6 of them, offshore of Delaware, and it got turned down, so that is not happening either. So there's not much going on in Delaware. Maryland, a lot is going on, Virginia, but New Jersey just made a major step back, so they're not going to build anything in New Jersey. So every state is at different stages. Cape Wind has just made some major progress 2 weeks ago. Yet another permit was achieved.
Well, a company on Long Island tried, and off Jones Beach.
I just heard about it this
That was
morning.
turned down, and people don't like seeing these things.
That's right. So my university has done a lot of work on people's perception of offshore wind, and there's all kinds of theses that we interviewed people. We made pictures with what the turbines will look like offshore of your beach. How much are you willing to pay? Because they were saying, oh, tourists are not going to come because they see these ugly turbines. So they interviewed tourists, and they would say, you know, if you saw this, how much of a discount would you want on your hotel rate to actually come? So they were trying to quantify. I mean, are we just talking about complaining for the sake of complaining? But, you know, it boils down to, you know, how much does it cost? Come on,
What about the bird people, migrating birds? Sorry.
I think we can have this discussion later.
Okay.
It's 1:15, because you have a schedule to
Yeah, I have to go.
So let us thank Cristina for such a wonderful time.